So, we introduced, I will just go back and introduce the creation operator first, that if it acts on a vacuum state, it gives you a state which has the ith spin orbital, okay. And then if you add AJ dagger on this, then you make a determinant which is Ji, which means essentially it is a determinant, J is the first column. So, this is the rule of creating electrons, and then we found that the AI dagger, AJ dagger plus AJ dagger, AI dagger is 0, the anti-commutator is 0, okay. So, then we are introducing the reverse operator, which is basically the annihilation operators. So, the annihilation operators do exactly opposite. First, to know that if it acts on a vacuum, it simply gives you 0, because it cannot annihilate, nothing is there. It, however, if it acts on a state or a determinant which has chi I on the left and then whatever is there, chi I and then let us say chi 1 etcetera to chi n minus 1, then it generates a state which is chi 1 to chi n minus 1. So, the idea is that these are annihilation operators which immediately remove a spin orbital exactly to the right, immediately to the right. So, these are called annihilation operators. What we wanted to show is that these annihilation operators are adjoint of the creation operators. Okay, so that is what we wanted to show. So, this is the definition of the annihilation operator. Why is it an annihilation operator? I have written now in AI, but of course, this is AI dagger. So, it is deliberately written because I will now show that they are adjoints of this. So, we did that last time. So, let us take a determinant which is AI dagger, AJ dagger, vacuum. So, exactly negative of this, okay. So, let us take a 2 electron determinants AI dagger, AJ dagger, vacuum. So, that is IJ, right. By definition, first J will be created, then I will be created. Is it okay? So, I can write this as AI dagger, then I can write this as AJ dagger vacuum, which is AI dagger J. The same state K I am writing as AI dagger J, because AJ dagger vacuum is a state where only one electron is there in chi J orbital, correct. So, now let us take this conjugate of this. So, let us write this conjugate as J AI dagger dagger, right, and I will call this J AI. I will show that this AI is an annihilation operator. Okay, right now this AI is just a conjugate of AI dagger, do not interpret it as an annihilation operator, okay, because I will show that they are actually adjoints of the creation operator. So, I just write this as J AI, is it okay? So, then we do the normalization of Kk. What is the value of Kk? Because K is a 2 electron determinant, Kk is 1, right. Because all these determinants are normalized, they are all orthonormal orbitals. So, Kk is 1. So, I write for the conjugate K this J AI, and on the right side I simply write K. So, this k is written as JAI and the right side I wrote just the k. Okay. So, now I am going to interpret JAIK is equal to 1. So, what can be 1 unless this itself is J, right. So, I made this 1 in two ways. One is this determinant normalization is also 1, 2 electron. Another is the orbitals are also normalized. So, now I propose that the AIK must be equal to J. At this point, AI is not an annihilation operator. AI is simply adjoint of the creation operator, right. But now I am showing that this AI acting on K must give you J. So, what is my K? K is Ij. So, AI acting on Ij must give me J. Hence, I show that the AI is a annihilation operator. And it annihilates exactly the next to it. So, both these rules. Okay. So I initially, of course, yesterday I discussed the annihilation operator, but I have not showed. I am now showing. Yesterday I was showing it actually, but probably did not complete it. That why are they adjoints of creation operator? So, to show this, I just take a 2 electron determinant and then write this as AI dagger, AJ dagger vacuum, which is J, and write this the conjugate of K as J AI dagger dagger, which is now defined as J AI, but this AI need not be an annihilation operator. Then I show that the J AI K must be equal to 1, which means AI K must be equal to J, which essentially means that AI annihilates on a spin orbital I from K. Is it clear? I hope everybody gets the logic. It's a little involved logic, but it's easy. You can, this is a 2 electron, but you can show it in many other ways. Okay. So, essentially if you show this, then it is easy to show the anti-commutation AI AJ equal to 0, just by taking the conjugate of this. This I have already proved. I can prove it by showing that this is an annihilation operator in the same way. Yesterday I did that, but a simpler proof is just to take a conjugate of this. As soon as you understand that the annihilation operators are nothing but adjoints to the creation operator. Okay. Then we will ask the question, what happens if I have a commutation between two operators, AI and AJ dagger? So, one of them is creation, one of them is annihilation. What happens to the anti-commutation between these two operators? Okay. These parts are clear. Any I and J, it is 0, and of course, specifically also for I equal to J. I equal to J essentially shows that you cannot destroy twice, because AI becomes 0. So, you cannot destroy twice. Okay. So, remember the anti-commutation here is very important. If this was a commutation for I equal to J, you would not have got anything, because it means AI minus AI is 0, that is a triviality, right. So, you would not have got the new physics. So, here the physics is that if I equal to J, AI plus AI is 0. The plus is important. If it was a commutation, then of course, it is trivially 0. So, I don't get a new physics. You understand? Here, because of the plus, I can now show that AI must be 0. It's a null operator, which means I can't annihilate twice, just as I cannot create twice the same orbital. So, this is why the anti-commutation is very important. The fact that I have an anti-commutation relation and not a commutation relation, because commutation relation would not have given this, because that would be an identity for I equal to J. Okay. So, let us ask this question now for AI AJ dagger. Let us do it in 2 steps. So, let first I take I equal to J. So, it means I want to define what is AI dagger plus AI dagger AI, right. So, I am asking this question of AI AJ dagger or AJ AI dagger, whatever, for I equal to J. So, I have the anti-commutator, which is now AI dagger plus AI dagger AI, correct. So, quite clearly let it act on a general determinant. So, I will find out what happens if it acts on a general determinant. So, there are 2-3 possibilities. Let us say the determinant contains chi I, okay. Then of course, this will act, but this will not act, okay. If it does not contain chi I, then this will act. If it contains chi I, then this will act, this will not act. So, only one of them will act, okay. So, let us take this AI dagger when the determinant does not include chi I. So, what will it do? It is a very trivial thing. It will first create and then it will annihilate. So, I will simply get back the determinant, correct. And of course, if AI dagger AI acts, it will be 0. So, if chi I is present in the determinant, then I can say that the anti-commutator AI dagger acting on the determinant is equal to the same determinant. If I is present in the determinant. So, that is a simple way of writing. It is a simple group notation that I is included in the determinant, okay. I is not included in the determinant, that is what I proved, okay. So, then of course, AI dagger will first create and annihilate. The next is I is included in the determinant. If I is included in the determinant, then of course, the first one will not act, that will give you 0. So, what will act is just AI dagger AI. So, AI dagger AI acting on the determinant, and let us say now the determinant is something like this, chi I some chi n. So, chi I is included somewhere, I do not know where, somewhere it is included. However, to let this act on chi I must bring chi I here. So, a simple way to do that is to flip k and I. So, I get minus AI dagger AI chi I chi k chi n. So, simply replace k by I. So, two columns of a determinant just changed, then of course, it is just a negative sign. So, then I can allow AI to act on chi I and then make AI dagger here. So, I will get back minus chi I chi k chi n, correct, because I will first annihilate and then create, and then I push it back again here. So, I will get chi k here, chi I here, chi n here with the plus sign. So, exactly as it was, right. So, I first push it by, let us say my first column was k, some k, and I arbitrarily lies somewhere. So, I first change this to first column, then I annihilate and create and then push it back. So, the two negative signs will again give me positive, and the other one will no longer act, AI dagger AI dagger. So, essentially I can again say that the commutator of AI dagger of this determinant is also the same determinant. So, these two is one I is included in the determinant, another I not included in the determinant. In either case, if the anti-commutator works on the determinant, it gives you back the same determinant, right. And of course, these two sets of determinants span the entire set, because either in a determinant I is present or not present, that is only two options, right. So, then I can say for any general function, if this anti-commutator works, it will give you back the same function. So, in one case, one part of the anti-commutator is working, in another case, the other part of the anti-commutator is working, okay, among the two. So, I can now write that a relation that AI dagger is equal to 1 when I is equal to j. Then we come to the next case, if I is not equal to j. So, explicitly now we are talking of case B, where I and j are different. Remember that they are different now. So, we again look at AI AJ dagger now plus AJ dagger AI acting on a general determinant, and let us say when this will survive, when this will not survive. If you look at it very carefully, if either way j is present and I is absent, it will not survive. Because if j is present and I is absent, this cannot act, neither can this act, because j is present. So, I can't create, right. And in fact, if either of them is true, this will not act. So, the only time this will give a non-zero value possibly is when I is present and j is absent. Is it clear? So, this determinant can exist or give a non-zero value, this action can give a non-zero value only if I is present and j is absent in the starting determinant. Okay? Otherwise, it will become 0. Is it clear to everybody? Because then either AI will not act or AJ dagger will not act. And now remember, AI and AJ dagger are different. I is not equal to j. So, you can't say that no, I will first create and then annihilate. That is already done. They are now explicitly different. Okay? So if j is not present, if j is present, then of course, this will automatically give you 0. If I is absent, then this will give you 0, and this will also give you 0, because even if I create j, I can't annihilate I, because I cannot be equal to j. So, each of the strings will give you 0, each of the strings. So, there is, unlike in that case that either this will act or this will act, each of the string is going to be 0 unless both are true, which means I must be present and j must be absent, both must be true. Is it clear? Because you look at this string, it is AI AJ dagger AI, correct. So if this is not true, each of them will become 0, because if I is not present, AI cannot act. If j is present, then AJ dagger cannot act. Yes, that's what I and j, then AJ dagger will not act. AI will act, so what? Eventually, whole thing has to give you non-zero. You take a determinant AJ dagger AI, both I and j are present. So, let us take chi I chi j. Okay, so this will act, this will give me AJ dagger chi j. This is 0. See, eventually the string has to act, the product operator has to act. So, it is not a question of that this acts and gives you something. After that, what happens? Okay. So, this is the only condition in which this will survive, and let us analyze what happens then. Is it clear? Because I have already eliminated I equal to j case, I have shown that this is equal to 1, AI dagger AI equal to 1. So, now you cannot say that I will create and annihilate the same orbital, because there are two different orbitals. Now, explicitly I is not equal to j. Okay. Is it clear? All right. So, let me now take that determinant. So, my determinant is I is present, j is absent. So, I have AI AJ dagger plus AJ dagger AI on a determinant which is now, let us say, generally chi k etc. Somewhere chi I is there, exactly like the way I write chi L or chi N, whatever. So, I am just marking chi I is an arbitrary orbital which is now present, And of course, very importantly, j is absent. So, j is absent. So, let us see now how do I do this. Before I even start this problem, let me bring chi here, because I know I have to do that. So, let me write this as a minus ai aj dagger plus aj dagger ai with chi I here and chi k here. So, all I have done is to interchange chi I and chi k. So, that is you do not have to bother about how many operations are there, just interchange. So, my whole impetus is to bring chi I right in the beginning. So, now let us allow each of these operators to act, and then we will sum, and do not forget the negative sign. Okay. So, when aj dagger ai acts, what happens? You annihilate I and immediately create j right here. So, I is replaced by j, correct. And when ai aj dagger comes, again j comes, but then I have to first interchange chi I to annihilate. Okay. So, let us do this first. So, ai aj dagger chi I chi k chi l. So, what is the result of this? I first have ai, then I have one electron extra now, because I am allowing aj dagger to act. So, chi j, chi I, chi k, chi l, correct. Then I interchange. So, I make it minus of ai, then chi I, chi j, chi k, chi l. Okay. Now, I can annihilate chi I. So, this is gone. So, the result is minus chi j, chi k, chi l. So, what did I do? I said if ai aj dagger acts on this determinant chi I, chi k, chi l, it will give you minus chi j, chi k, chi l, because of the fact that I am first creating j and then annihilating I. I had to do another interchange. I have a negative sign here, so do not forget it. So, that I will do at the end. Okay. So, the next is aj dagger ai. So, aj dagger ai acting on the same determinant now chi I, chi k, chi l. Remember, I had an arbitrary determinant. I have first, this negative sign is to bring chi I here, okay, with chi k, interchanging with chi k. Now, this is easy, because simply I is annihilated, j is created. This is very easy. If you first annihilate and create, all you do is to create in that place, okay. By interchanging you can easily show this. So, this now becomes chi j, chi k, chi l, okay, exactly like this determinant, but without the negative sign. Now, it is very clear, either I take the negative sign or does not matter, it is 0. The sum of these two is 0, because it is the same determinant with the opposite sign. So, of course, I can then conclude that ai aj dagger plus aj dagger ai acting on this determinant, where what is this determinant? This determinant is where I present, j absent, remember explicitly, is also equal to 0. And we have already noted in all other cases, this is anyway 0, the anti-commutator is 0, that I have already noted, that it will survive only for this case, but even in this case it is 0, right. So, I can then say that if I not equal to 0, by again the same argument that any given state can be expanded in terms of all the sets of determinants, I can argue that the ai aj dagger is equal to 0 if I not equal to j. For the case of ai dagger ai, it is fairly simple, okay. That is, if there is a I, you annihilate, you bring it, annihilate and bring it back, so it is same. If I is, that is if I is present, if I is absent, this ai dagger ai will become 0, but then the ai dagger will act. So, either one of these two terms will be there, depending on chi chi is there or not there. And in each case, you will get back the determinant. So basically, the sum of this is equal to 1. So either 0 plus 1 or 1 plus 0. So if chi is present, then if chi is present, then this will act, AI dagger AI. First it will annihilate, then it will create. You can't create first because chi is already present. So the question is that if chi is absent, this will act and the other one will not act, right? Question is what you do first. That is very important. I am AI dagger AI, of course, means I am creating and annihilating the same orbital, but what you do first is very important. So depending on this will survive, one of these two terms will survive, but since you are talking of plus an anti-commutator, anyway one of the terms will survive to give you 1. Whereas for I not equal to j, I showed everything anyway becomes 0, only if I is present, j is absent, it can survive, but even in this case, I showed that this is equal to 0, okay. So first we had shown, remember AI dagger, AJ dagger equal to 0 anti-commutator. Then I argued that the annihilation operator that we defined are the adjoints of the creation operators. I showed this today. So then of course the anti-commutation relation of the annihilation operator comes straightforward from the adjoint to the creation operator. And then I showed the anti-commutation between one creation, one annihilation operator, which essentially takes care of everything. So this particular thing can now be rewritten as, of course, you know how to rewrite with a Kronecker delta, right? So don't forget your Kronecker delta. So whenever this 1 and 0, so I want to avoid. So eventually, of course, it is just delta ij, and then delta will take care. Is it okay? Let me ask the question. Can you show that two spin orbitals, chi I and chi j, of course, we know equal to delta ij, and this is the cornerstone of our anti-commutation relation. But can you show this now by second quantization? You understand the question? Can you, if I just ask, show using the second quantization anti-commutation relation, show that, because obviously the anti-commutation relations are based on orthonormality. So now orthonormality you should be able to prove by anti-commutation. So I am just reversing the problem. Remember, it is a Kronecker delta. So if I equal to j, it is 1. I not equal to j, it is 0. So now you know. We just now did. Huh? I hope all of you can do it, but let me just solve it. So what is chi I adjoint? It is vacuum AI. Because remember, what is chi I? Ket. Chi I ket is AI dagger vacuum, correct? So what will be the conjugate chi I? Vacuum AI dagger dagger, and I have shown that this is annihilation operator. So it is vacuum AI. So the annihilation operator acts on the left of the vacuum. Creation operator acts on the right of the vacuum. Annihilation operator cannot act on the right of the vacuum because there is nothing to annihilate. But left it will act because of an adjoint. Then I write chi j. It is AJ dagger vacuum. Correct? So I am writing the left hand side. So vacuum AI. Now what will you do? You will actually go back and use this anti-commutation. Right? So how do I write the anti-commutation? AI AJ dagger, remember the anti-commutation. AI AJ dagger equal to delta ij minus AJ dagger AI, correct? Remember how to use this. AI AJ dagger plus AJ dagger AI equal to delta ij. So AI AJ dagger is delta ij minus AJ dagger AI. So let me put this here. Vacuum, I am just writing V to simplify. V delta ij minus AJ dagger AI V. Correct? Now look at the first term. Delta ij is a number. Kronecker delta is a number, either 1 or 0, doesn't matter. So it comes out, and vacuum expectation value is norm is 1. Correct? So vacuum also is normalized state. So you have just delta Ag minus vacuum Az dagger Ai vacuum. Correct? Is it okay? And now you see Az dagger Ai acting on vacuum is 0 because Ai cannot annihilate. Neither can Az dagger can act on the left. So this is 0. So the result is delta Ag. Note what we are doing is that based on the orthonormality we already did this anti-commutation relation. Now I am reversing the problem. I am saying the anti-commutations are God. Once I have anti-commutation relations, I do not need to know anything else. That is the whole idea of second quantization. Can you now construct everything from the anti-commutation? So including the fact that the spin orbitals are orthonormal. Because if my anti-commutation is right, the spin orbitals must be orthonormal. Okay? So the creation of the electron in those spin orbitals must be orthonormal. So I am just trying to prove that chi I chi j equal to delta Ag. So I hope you see how the proof goes. Okay? Okay, let us take another problem which I wanted to take first. Remember, among the most used anti-commutation, you will actually need to know this. This will be the most used anti-commutation, most useful anti-commutation. And this is written in this form. Ai Az dagger is delta Aj minus Az dagger Ai. Of course, this could have been Az dagger Ai, this could have been Ai Az dagger, does not matter. They are plus, so it does not matter. So now let me take another problem. Yeah, so let us say given a determinant K, so given a determinant K which is chi 1, chi 2, chi n, that is like a Hartree-Fock determinant, right? It is a Hartree-Fock determinant or whatever determinant, does not matter. How do I write this? I write this as A1 dagger, A2 dagger, An dagger, correct? Vacuum. Remember, this is how I have to write it. The first one will come actually last because I am building the first column with An dagger, then N minus 1 dagger, etc., A1 dagger. So just please learn how to write this, just looking at the determinant. The order is very, very important because if you interchange, then there will be sign change. Okay? So this determinant can be written this in terms of V is just a short form of vacuum. Okay? So that is a given. Now we want to show that K Ai dagger Aj K equal to 1 if I is equal to j and that orbital I is included in the subset of 1 to n. Okay, I hope you understand. Is 0 otherwise. Otherwise means otherwise. So I hope specific things you should be able to understand. If I is equal to j, I am annihilating Ai, so Ai must be included here, otherwise I cannot annihilate, right? Okay. I am now saying that if otherwise, what happens if I is not equal to j, then what are the other possibilities? That I can annihilate j here, okay, and then if I annihilate, I have to create, but I cannot create if I and j are in the subspace. So the only thing to understand is that both I and j, I should also write, both I and j are in the subspace of 1 to n. So of course in that case I cannot create. So you can physically understand. So that is my I and j. I and j are basically among the 1 to n orbitals. So in such a case, it is equal to 1 if I equal to j and 0 otherwise. That means if I is not equal to j, it will become 0. All right.